Sergio Doplicher, and since about half of the people in the audience seem of such an age that they weren't born yet when Sergio wrote his first papers, I would like to mention at least a few highlights. The first work I'm aware of was on covariance algebras, or cross products, with Kastler and Robinson, which was very influential. And then there came the magnificent series of papers by Doplicher, Haag and Roberts that were already mentioned. Culminating in the work by Doplicher and Roberts on the reconstruction of the gauge group, I would like to emphasize that I believe that that's the first use of category theory in physics, and more generally the whole style of reasoning was, I think, completely new in physics and even in mathematical physics. Then later on Sergio worked or introduced even the split property, the notion of localized charges in a certain sense. He was also one of the pioneers of quantum field theory on non-commutative spacetimes, and I'm sure we'll hear new ideas by Sergio even now. So the title is The Principle of Locality, Fate and Challenges.
Thank you very much, Klaas, for this so kind introduction, and also would like to thank the organizers for this privilege and honor to talk in this nice occasion, which is to celebrate the 50 years of this great idea of Rudolf, which actually was formulated in public first in 57. So in a way, this is a way of honoring Rudolf. And I would like to mention that 57 was also the year of passing of von Neumann. So in a sense, it was a rebirth of von Neumann in algebraic quantum field theory, which started in that year. But we are here, I should like to mention also, for another great occasion. There is a reason why I wrote it in Roman letters, Detlev. And the reason is that if you permute the letters, you get light. And of course, everybody knows Fiat Lux, which in the original read, Vayomer Elohim Yechior Veyechior, yeah? Which means that God said, let there be light, and there was light. But did he say that? I think he thought this. But you know, God is a quantum field theorist, and I'm sure he likes algebraic quantum field theory. So probably he thought of that and of gauge theory in terms of local algebras. That's precisely what we don't know how to do. But Einstein said that when he was asked why he does physics, he answered, I would like to know the thoughts of God. So my best wish is that to go on this road. Thank you. Well, as a joke, I would like to point out that not only this date is a round date for locality, but in my own personal career, I discovered, thinking of this talk, that it is an important day. Nonetheless, today I have absolutely nothing new to say. No result. I have to tell you only opinions, and mostly they will be heretic opinions. But maybe for the last part, some of these heretic opinions are already shared by somebody since a long time. In that case, they will be bored. Especially, okay, I'll tell that at the right moment. Anyway, this is the plan of the talk. I will first talk of the Planck scale, which refers to the fate of locality. And then I will talk of something which refers to the challenges, namely massless particles. I will be very brief on that. And the EPR, Einstein-Podolsky-Rosen paradox, and the quantum theory measurement. And I think there is an interesting challenge there to be taken over. Okay, for the fate of locality, I think the fate is the same as the phoenix bird. Not after 500, but maybe even after 50 years, to be burned to a new birth. Yeah? And the reason why I think it has to be abandoned or reformulated or reinvented is the same reason why I believe that space-time in the Planck scale is quantum and not a classical manifold. Namely, And that's the reason why you have to abandon locality. Let's just think to the localization of an event, which I describe symbolically by the operation tau on some quantum state of our system. Yeah? So the effect of localizing an event with some uncertainties in space-time will be to change your state from the state omega to some state tau omega. Yeah? Now, this state is a quantum state, and it will have some energy momentum densities, mean values, which were omega of T mu nu before and tau omega of T mu nu after. If you want really to claim that you localize your event with those uncertainties, you have to demand that if this equation had no singularities, no closed trapped surfaces before your measure, there should be also no trapped surface created by this new contribution to the energy momentum density due to the localization measurement, which would trap your localization region inside. Otherwise, for a distant observer, no signals could come out, and it would be an empty statement to say that uncertainties were what you claimed. Yeah? So this is a sort of a principle which limits the possible uncertainties. Yeah? And to make this principle to a quantitative statement, one should have to solve exactly this, the semi-classical equations, which is plainly impossible. So the best you can do is to solve some approximation, and the best you can do is to take the linear approximation, but also there are no good workable conditions to describe, to prevent the formation of closed trapped surface. That's also a very hard problem. Yeah. So the best you can do is to use the linear approximation and use some primitive condition. The primitive condition we used in a work with Klaus Haag and John Roberts 15 years ago is the condition that if you start with a flat Minkowskian space-time, you solve your equation, you find some deviation of the metric from the flat metric, this deviation should never become negative. The 0,0 component should never become negative. If you think of it a moment, this is exactly semi-classically as the condition that the photon cannot escape because the total energy has to remain positive up to, I mean, taking only orders of magnitude, of course, because you get a 1/2 rather than 1 from general relativity. Anyway, if you use this condition and you tackle these problems in some simple free field models, you end up with a bound for the modulus of the potential which is created of this form. So in flat space-time, in the vacuum, rather would say, you have the condition this phi should be of modulus smaller than 1, and then you have this should be bounded below by the order of 1. Yeah? More generally, you would have to take, in the linear approximation, you have to take the G00 due to tau omega as the sum in this linear approximation of these two terms, and the condition, a bound you would found would be these funny relations on which I will comment later. But let's now take the case where you are in the vacuum. Then you have 1 on the right-hand side, yeah? And then you want to implement these uncertainty relations with commutation relations. Let me, this uncertainty relation just tell you that you cannot use C number or classical variables for the coordinates, but you have to use operators which are based on commutation relations, which should implement exactly this uncertainty relation with 1 here. Yeah? Okay, this was done in this work of 15 years ago, and the quantum condition we found, which are working perfectly for this purpose, were rather simple. You have to, you may suppose that the commutator is central, and you may suppose that these two tensor given by the commutator contracted with itself is 0. The only thing which has to be non-zero is this funny invariant, which I take in the square because otherwise it's a pseudo scalar, not a scalar. Yeah? And then you get up with the model of quantum spacetime, which exactly implements this uncertainty relations, but which is completely invariant under the full Poincare group. Yeah? Okay, this is just quantum condition sum operators. We would like rather a sister algebra, which is the quantum deformation due to this physical reason of the continuous functions falling off at infinity on R4. And then how do you get from this to sister algebra? Well, you first take this commutation relation in the Weil form, because you want to irregular representation, and then take the enveloping sister algebra of the Weil relations. And the result, after a bit of work, is that this enveloping sister algebra is just a trivial continuous field of the algebra of compact operator on separable Hilbert space based on a manifold which is just defined by this same equation when you put in the place of the commutator a generic real antisymmetric two tensor, C number. Yeah? And then you get an equation for a manifold, and this manifold is sigma. It's just a quotient of the SL2C by the diagonal. Okay, now you get a model to which an algebra to which the coordinate operators are affiliated in a natural mathematical sense, and which carries an action of the full Poincare group, which acts as a shoot of the coordinates. And important for us will be the center of the multiplier algebra, which is just the continuous bounded function on this infinite manifold sigma. Yeah? Okay, this coordinates Q describe one event. It's the new geometrical basis to start on where you want to develop quantum field theory, which takes into account some minimal effects of gravity in presence of quantum theory. Okay, now, if you want to consider more events, you should take, as usual in quantum mechanics, tensor products of copies of this system, but it is wiser to take the tensor product not over the C numbers, but over this center. What does it mean? The commutator itself is affiliated to this thing, yeah? So this means that you just stipulated that the commutator is the same at all spots in the tensor product. Yeah? With this choice, yeah, you can consider the minimal Euclidean distance between two distinct events, which is just given by this operator, sum of the squares of the coordinates of qj minus qk, and you find out by a simple generalization of a computation we had in the first paper that this is bounded below by something of order 1. 1 here means, of course, in absolute units, so the distance 1 is the Planck length. Yeah. Okay, so this is very interesting from the physical point of view because it gives you a relativistic model, yeah, where the minimal Euclidean distance, which is not an invariant, but is always bounded below in all reference frames, which contradicts some statement that you currently find in the literature, the minimal distance is in conflict with relativity. Okay, now, this difference operator, which enter in the distance, can be interpreted mathematically as a picture of the differential and the universal differential calculus. This is not so. This is a universal calculus which is not so universal because it took this quotient modulo the center first, and second we stipulated that the differential of the identity is 0, which is a sort of a limitation. But apart from this, it's quite a general calculus. Yeah? And to work with this calculus, it's better to work with the following algebra. This is the direct sum of all the tensor powers of E with itself as Z modules, but you take it not only as a space, but as an algebra with this funny tensor operator, which you might well call the E bimodule tensor product. Because you see, when these two factors touch, you use not the tensor product, but the product in the algebra E. Yeah? This is the right algebra to work with if you want to compute with the differential calculus. And why is it so useful? Because this has two different algebraic structures. It has the structure of a sister algebra, which is just the direct sum of sister algebras, if you complete it in an appropriate way. And it has this structure of a star algebra, which is appropriate for the differential calculus. Why do you need the two? Because if you want to evaluate measures of differential operators, you have to take the norm in the sister algebra direct sum. But when you compute the algebraic relation, you have to take products in this algebra. So I just mentioned briefly what you find with this algebra. I said already that our condition tension product just means that the differential of the commutator is 0, yeah? And the differential of the Q is just the difference of the coordinates of two distinct events. Yeah? Then, as I said before, if you look at the minimal distance, Euclidean distance, you can express it. Actually, there is a mistake. No, that's all right. You can say that this sum of modulus square in the sister algebra I mentioned is bounded below by 4. Yeah? But then you can go on from distance to area and volumes. And this is quite interesting, because if you compute the area operators, space area, or the time space area, you find that they are bounded below by 1, always in absolute units. Then there's something more funny. Oh, first of all, why did I put here the modulus? Except the distance, all the other operators, area and volume operators, are not self-adjoint operators. They are only normal operators. It's not even clear why they are normal, but certainly it's clear why they are not going to be self-adjoint. Think of the volume of a solid. If you permute two vertices, mathematically this means that you change the order of some operator which do not commute. And then there will be an additional term which is I times something, which is the commutator, which is Q-adjoint. Yeah? So the operator itself cannot be self-adjoint, right? Except the case where you cannot permute anything, you have just one factor. Yeah? What is less obvious, and actually is, I don't know any a priori reason why all the operators we write down turn out to be normal operators. Yeah? So they commute with their adjoint, or if you want, they have the form A plus IB, where A and B are commuting self-adjoint operators. Why should they commute is not entirely clear. Anyway, if you go over from the area to the 3 volume, you find something which is slightly surprising. The spectrum of this operator, which is a normal operator, is the whole complex plane. But if you go to the 4 volume, you find an interesting spectrum, which is well separated by a quantity of order 1 in absolute unit from the origin. This means that the minimal volume is of order 1 in Planck units. But the spectrum, the rest of the spectrum is rather complicated, as you can see here from this formula. All these results that I mentioned on these slides are an unpublished, yet unpublished work with Klaus Friedenhagen, which we hope will be, I should say, yet unwritten. It's written down, but not written up in the Addison language. Yeah? But it will be written soon, I hope. Yeah? Now, this is strange but not surprising, because if you think a moment of our uncertainty relation, you see that by a very naive intuitive argument, you have to expect exactly this, because this is just the expression that the minimal uncertainty times the maximal certainty has to be in space, has to be of order 1. Yeah? And this gives you this area bound. But if you take the 3 coordinates, you forget about time, 3 space coordinates, you can very well make the uncertainties in 2 very small and leave the third as large as the product with the common value of the other is of order 1. This means that the volume can be as small as you like. But if you take into account the time coordinates, then the product of the time uncertainty times the minimum space uncertainty has again to be of order 1. So the product of the 4 uncertainties is again of the order 1. And this explains why the volume has this gap. The 4 volume has this gap. Okay, so I won't say more about this. It's just a hint how the quantum space-time might give you quite an interesting geometrical structure which has to be explored. But of course, this was just geometry. You want quantum field theory. Well, we indicated already in our first paper, I mentioned how to do quantum field theory. You define a field on quantum space-time. By the usual formula, you take the anti-Fourier transform or its Fourier transform, or the other way around. But in one direction, you use the normal Fourier transform. And going back, you use the Weil operators. And this gives you the von Neumann prescription of evaluating a function of this non-commutative quantity, yeah? Which works for the Schrödinger's Q and P and works here too. Yeah? Okay, so this gives you field operators which are affiliated to tensor product of some algebra fields and to the algebra of quantum space-time. And this is the natural thing to look at, because just the generalization of the tensor product of A, which is C0 over 4, which is just a different way of writing the continuous functions vanishing infinity from R4 to A. Yeah? So this tensor product is just the precise non-commutative notion of functions on the quantum space-time. And of course, this is not a real operator. You have to take the usual provisos that we know from Weizmann's theory. Okay, but once you have this, you can again define local algebras, even if you don't have the Minkowski space. Local algebras are defined, as we heard already this morning, as a map which sends nice regions in space-time to von Neumann algebras. Here, you have to replace the nice region by its characteristic function. The characteristic function is a projection in some algebra function, which is not the continuous functions, of course, but it's a Borel completion, if your region was nice. Yeah? And you have to do the same. You take some Borel completion of your algebra, you take, in the sense of Gert Pedersen, you take the projections in this algebra, and you take any self-adjoint projection here inside, and to that you associate the von Neumann algebra. How? You just take the field operators evaluated on quantum space-time, and you evaluate them on this condition expectation, which takes a state only on the E part. Yeah? And then you get your field evaluated at a state, which is the generalization of a point. Yeah? And then you take all states which are supported by E. Yeah? And then you generate a von Neumann algebra. These are the local algebras on quantum space-time. This is a nice notion which has not been exploited much, except in some, again, unpublished work with Klaus, where we studied a lot of ways to recover the classical algebras in the classical limit. It was a bit complicated, so I will not tell anything on that. I will just give you a striking example. If you take a free Fermi field, if you take the simplest projection you might think of, just the spectral projection of this operator Euclidean square of your coordinates associated to the minimum of the spectrum. So you just pick this discrete point out, yeah? It's not the discrete point, this minimum out, yeah? And then you evaluate the local algebra with that. It turns out to be finite dimensional, just because you have just one state left with that property. It's not exactly one state because you have to take into account the center, but the function you get with this omega of q is just one specific function, just a Gaussian. Okay, but if you take this local algebra, you translate it a little bit in space-time with the small neighborhood of the origin, you generate a von Neumann algebra with this translates, you get an irreducible algebra. So you have this striking behavior. Yeah. Okay, and one other thing to be mentioned on this local algebra, in the case of free fields, this net of von Neumann algebra associated to quantum space-time is fully covariant, yeah? But there is nothing like local commutativity, because the very notion of space-like separation loses its meaning, yeah? And it will lose much more its meaning if you introduce interactions. So in the case of just free fields, you could still have some meaning, spatial localization on wedges for special values of the central variables, but it's all going to be lost in interactions. On top of that, if you compute the commutation relation between fields evaluated at optimally localized states, but when the center of one moves away from the other in space-like direction, you find a commutator which is not zero in space-like direction, but drops out like a Gaussian. Yeah. So the locality is lost. What about interactions? You can introduce interaction densities, for instance, for a polynomial interaction by generalizing the usual formula, but again, you get that this is equivalent to from the point of view of scattering theory, to an ordinary non-local interaction on classical space, Minkowski space. So locality is lost in all senses. And also you meet on top of that problems with Lorentz covariance, which are not problems starting from the geometry, but from the interaction. Yeah? It's the lack of a proper formulation of interaction which preserves Lorentz invariance. There is something subtle you could do that we did with Dorothea Barnes, Klaus Friedenhagen, Gerardo Piacitelli, published back in the 2003, to redefine the Wick product as the quantum Wick product. When you take into account that if you take the ordinary Wick product at different independent events, you are not allowed then to put Qj minus Qk equal to 0, because, as I told you earlier, these are quantum variables which have a non-trivial commutation relations between the different components, and the Euclidean square is bounded below by something of order 1, so you cannot put it equal to 0. So the best you can do is to evaluate a state on the differences, on the algebra generated by the differences, which correspond to the lowest eigenvalue of sum of Qj minus Qk mu square summed over mu. Yeah? And if you do this, you can do this. This is given by an appropriate conditional expectation that we studied in that paper. Yeah? And you find out a new definition of the density, of the Hamiltonian density, which in the Gelman law expansions give you perturbative series with no ultraviolet divergences left. No ultraviolet divergences left at all. There is a price you pay that you have to take an adiabatic cutoff in time, which is very hard to remove. Yeah? And of course, there is a further price that in order to give a physical meaning to this, you cannot avoid the renormalization. Renormalization has still to be done. There has to be a finite renormalization, yeah, done in such a way that when you take the limit when lambda Planck becomes negligible, gives you back exactly the ordinary renormalization expansion, renormalized expansion. And this is also a hard problem which has not been seriously tackled so far. Okay. Now, I would like to come back very shortly before passing over to the comment I made at the beginning. At the beginning, I made that if you consider the effect of some background quantum state, not curved space-time, but you have a quantum space on Minkowski space, yeah, which has his own energy momentum density, it will give rise in a semi-classical approximation to some field, which is the solution of the Einstein equation, yeah? And then you have to take account of that as a background. And then if you take that background in account, you see immediately as a scenario which results from that you have to expect that the commutator between the coordinates cannot be a geometrical entity taken from outside, but it has to be in turn a function of the metric tensor. Then it has to be a function of the fields. Now, this scenario is really terrific. I would like you to consider for a moment this situation, because these are no longer conditions that you can put beforehand, but become equation of motions, which are coupled to the Einstein equation, if Einstein equations remain as such in the quantum domain, which we don't really know, and to the field equations, which are contained, the metric, of course, through the covariant derivatives in there. So all this is a terrific set of coupled equations, and this scenario would show something which I do believe rather firmly, also I'm far from knowing any specific form for this gadget, yeah? That not only geometry becomes dynamics, but which is the case in classical generativity, but in quantum generativity, algebra has to become dynamics. Yeah? In particular, if you believe for a second in the heuristic estimates I proposed before, the uncertainty relation would have this funny term G00 inverse on the right, or something more civilized which has the same motivations. Yeah? Anyway, out of this suggestion, I just take one indication, that what's here on the right becomes divergent near singularities. I think this is the part of the scenario which is, has to be expected. And if you take this particular formula just to get an idea of what happens, you see that its effect is of changing the Planck length to the Planck length divided by the square root of G00. which means this is exactly what was standing on the right in those uncertainty relations, has to be read as the range of acausal effects due to the quantum nature of gravity. So this scenario will tell you that near singularities, the range of acausality is not the Planck length, but something which diverges. And this is not bad at all, because this would tell you a deep reason why there was equilibrium in the cosmic microwave background, yeah? And the equilibrium problem disappears. You don't need inflation to explain equilibrium, because near the initial singularity, the equilibrium was established instantaneously, yeah? Because of this effect. Okay, but this is a scenario which has to be understood. I would say that in my point of view, this is the most interesting direction of future developments, but in which no substantial step has been taken. Anyway, one way or another, which is clear by this short discussion, is that the locality is lost. Is it lost forever in all form? Well, I believe that like the phoenix bird, locality will be born again in a new form after a marvelous song, yeah? And but we have no idea which new form might be, but what we expect, we ought to expect that there is some deep form of locality that we don't yet know, which is exact, not just an asymptotic. You can always formulate an asymptotic condition, but that gives you nothing, it's useless. You need a sharp mathematical statement. I believe that there is such a sharp mathematical statement which expresses locality at the Planck scale, and which becomes ordinary locality in the regime where the Planck distance can be neglected. But we have no idea what this might be. There is one possible vague hint that I would like to mention. If you think of ordinary locality, you might say, why interacting fields obey locality? Well, the free field obeys locality, but this does not mean much physically, yeah? And the fact that the locality of the free field is preserved is due to the fact that interactions are local, yeah? And why the interactions are local? There is a deep reason, that's gauge invariance combined with minimal coupling. Yeah? So one might hope that gauge invariance combined with minimal coupling can be formulated in a proper way in the non-commutative setting and be used as a form, as a replacement of locality. But there is a big but here. We don't know even in Minkowski space how to formulate local gauge invariance in terms of local observables. That was the problem that Rudolf mentioned this morning. And there are, of course, these nice results that Klaus explained us, but they're in the perturbative setting. I don't know of any sharp statement which is not perturbative, which expresses the mathematical phase of local gauge invariance in terms of local observables. If you know something, please tell me. Okay, so this is a very bad problem, and it tells you that what Rudolf said this morning is he kept telling me in the last 40 years at least, yeah, that this was the main problem of quantum field theory, to understand the local gauges in algebraic terms. It pops out again even in the Planck regime as a really fundamental problem. Okay, so let me say two brief words on chapter 2. Local quantum field theory is extremely successful if you assume that you are dealing with a theory where there are no massless particles. If there are massless particles around, you meet problems. Now, are there massless particles around? Now, the neutrino has left the scene since a decade or so, yeah? Now, it is massive. They are massive, okay. But there are still two candidates, the photon exactly and the graviton. The best estimate I know, it dates a few months. It comes from a paper by Goldhaber and Nieto, which is in the web in March 2009. I owe this reference to Nikos Mavromatos, who gave me a few weeks ago, yeah? And I can show you the paper. And you have this estimate. The upper limit of the photon mass is 10 to the minus 18 electron volts, and for the graviton mass is 10 to the minus 24 electron volt. So we can well believe that they are massless. Yeah? If you are interested in details, you can see this paper, which looks like a very pleasant paper to read, by the way. Anyway, so there are many problems we meet with massless particles, especially with electrodynamics. It could be that the algebraic theory of superselection sector statistics extends, yeah? But this does not mean that we have understood the local gauge transformations, of course. As far as I can see, there is something which is very nice in the classical domain and becomes intractable in the quantum domain. And this is precisely the concept of local gauge invariance. It becomes intractable in the algebraic quantum domain when you want to keep the positivity of probabilities. Okay, one step is to go to indefinite Hilbert space, and we know all that. It becomes very complicated. If we want to keep the discussion within observables on positive metric, it becomes local gauge theory seems to be intractable, and despite the fact that physically they seem to be the real key to understanding nature, if you think of the standard model. But there's something very similar with general relativity. If you think of the general coordinate invariance in general relativity, which is the key point of the formulation of general relativity, well, mathematically it poses very similar problems. But also physically, myself, I will consider it is doubtful, because it's based on a Gedanken experiment, which is the Gedanken experiment of the Einstein's falling lift. This is a wonderful classical idea, but in the quantum world, if the lift becomes of the size of the Planck scale, our poor experimenter will not have much possibility of doing experiments inside. So this suggests that the principle might turn to something completely different at the Planck scale, but we don't know, of course. Okay, unfortunately, I don't have anything more to say on chapter 2. Now I will come to chapter 3, namely the measurement process. I think there too, there is a challenge to be taken for the principle of locality. Let's review a moment very shortly the measurement process in the classical formulation. We know that we have two types of change on states, the Schrödinger evolution, which is irreversible and unitary, and the changement when you measure a projection or an operator, say, with finite spectrum, yeah? Then a state omega is changed, a pure state even is changed to a mixture by this famous formula. Yeah? So you have this drastic change, pure to mixture, and if you if one of the specific values is recorded, you have the phenomenon of reduction wave packets. The other components are suppressed instantaneously over the whole space. And this suggests something non-local. In fact, the Einstein-Podolsky and Rosen paradox was exactly based on this. I will very fast review that for you. If you have, say, putting it in the language of local algebras, if you consider two spatially separated regions which are very well spatially separated, then there will be type 1 factors which include one and the other, which still commute with one another. So these two type 1 factors will generate a tensor product in the Hilbert space. Now, this comes, for instance, from the split property. If you take your observables, one in the first region, the other in the second region, then you have your vectors in these Hilbert spaces where n1 and 2 leaves, which are eigenvectors of those projections. And then in the tensor product, you can construct, if you like, this entangled vector state, but n1 and n2 generate a subalgebra of your quasi-local algebra. So you might well take this as an entangled state vector over the whole quasi-local algebra, which is entangled when it is restricted to this algebra. Okay, now say if O1 is here now and O2 is on Andromeda now, you measure EJ here now, you find the value, the J's value, and you say, haha, now on Andromeda, my pal is measuring B, and he found also the J's eigenvalue, the corresponding operator, which this is Einstein-Podolsky-Rosen paradox, which is a reformulation of it at least, which of course sounds absurd. Yeah? And it sounds like a sort of a very serious non-locality. Of course, the most common view is that this effect is based on an axiom of quantum mechanics, the axiom that when you measure an operator, you can do that instantaneously, and if you record one particular value, the state is reduced instantaneously over the whole space to that component. Yeah? This is an axiom. And the other point is locality. And people say they are not in contrast because you cannot use Einstein-Podolsky-Rosen even to transmit information. You cannot use it for anything, but still it exists. I will present to you another heretic view besides the heretic view on the distance of extension of causal effects in quantum gravity, which is that this statement is not true. My statement, which might be not new at all, is that Einstein-Podolsky-Rosen phenomenon does not exist. The reason is that the measurement process that I described for you has, in my view, has not to be taken literally. That description is only a very naive limit where you took the following limits. The duration of the measurement process is 0. The number of molecules which are making up the amplification part of your apparatus is infinite, and the volume occupied by the microscopic part of your apparatus is infinite. Or if you take these three limits, you may say what I said. But if you take none of these limits, your measurement will take place here. Your amplification apparatus will be here in a larger region, and the effect of the whole operation will extend in space and time, propagating with the speed of light. This is the picture. Okay. How much time do I have still, class?
20 minutes.
Okay, that will be quite enough. Thank you very much. So I started telling you that there is this big difference between the time evolution and the reduction of wave packets in the measurement process. Yeah? The first step to fill up this gap has been made in a very, very nice way by von Neumann, just for a change. Yeah? He said how you can reduce a way to reduce the process 2 to process 1 by considering the states of the composed system, the observed systems, and the apparatus. Yeah? Then you have a Hilbert space for both, and you have a tensor product of the two Hilbert space for the composed system. Yeah? Then you have to look at the total Hamiltonian, which will be the Hamiltonian of the system, the Hamiltonian of the apparatus, and the interaction which determines the measure. And the idea for Neumann was that it is enough to look at the evolution between 0 and t, a finite time, and this v will be responsible for the full measurement in this finite interval, but t will be so short that you can even neglect these two parts because the change in the normal evolution of the observable itself and the observable of the apparatus is not important. Yeah? Okay, then the evolution of the time interval t is given just by the Schrödinger operator e to the I vt, and then comes the crucial point in the von Neumann discussion. This evolution has to act in the following way. There is a distinguished state vector for the apparatus which gives you the state ready to measure A. Yeah? So your composed system is originating some states for the system itself, composed with the state ready to measure A of the apparatus. And the composed system, the state is described by the tensor product. If the state you start with of the system was already an eigenvalue of your projection operator Ej, then under this evolution, the first factor does not change, and the second factor becomes some state psi j, which means that the apparatus tells you, I read the j's value. Yeah? So that's the position of a counter or whatever, yeah. A click in a counter, etc. And of course, these states psi j are orthogonal to one another. Now, if you apply this by linearity to any state, you get, of course, this result. You get just the sum over the projections of psi along Ej, tensor psi r, which changes into the sum of the project of Ej psi tensor psi j. And remember that psi j are mutually orthogonal. Now, if you take this vector, it is, of course, what happened? This was Schrödinger evolution. Change a vector to a vector by a unit evolution. But there is something subtle here, that your original vector was a product vector. And the final vector is no longer a product vector, but in the language which is so much, that most people like so much, is an entangled state. Yeah? This means that if you take this entangled state vector and you evaluate the mean value of an observable alone without putting anything on the second side, then if you develop your scalar product, you get the scalar product psi j and psi k, which is a delta, and then you get back your mixture. This is just a well-known fact to anybody who studies rudiments of von Neumann algebras, that the normal state of B of h are just the vector state of B of h tensor 1 if you take 1 big enough, on an infinite dimensional Hilbert space. Okay, but now at this point we just shifted the problem a bit further, because von Neumann now asks, how do we know that the j value has been read, and why do we forget about observables of the apparatus? And he said these two steps are taken because you have three terms, the system, the apparatus, but then he wondered, but where does the apparatus end? The apparatus will have some microscopic part, then some amplification. This amplification will hit my eye, my ears, whatever. Where do I put the cut? He said, well, the cut is the consciousness of the observer. And this is the weak point, because he said it is the consciousness of the observer which chooses something, and this determines the choice of one of these values and the passage from the pure state to the mixture. Okay, so this was not very much appreciated by the physics community for a long time. There were lots of work. I don't know, maybe Steve knows the story very well. I don't know the whole story. I know what to me is a milestone. Also, I admit I never succeeded to read the original paper. But the milestone to me is a paper by three Italians, Daneri, Loinger, and Prosperi, in 1962, I guess, which proposed the different thing. Proposed the effect of statistical mechanics has to be taken into account. Namely, they proposed that the threefold decomposition von Neumann is not that one, but another one. System, microscopic part of the apparatus, plus the macroscopic part of the apparatus, which has the role of amplifying the result of the measurements to our scale. So this macroscopic part will be done by a finite but enormously large number of particles. Then you have to take the tensor product of these three Hilbert space. You have to take into account another interaction besides the previous one, which is the interaction between the microscopic and the macroscopic part, which gives rise to the amplification. But this is my own presentation. As I said, I did not read the original paper. But the important point is that there is no interaction between macroscopic part and the system. Why? Think of an example. You want to measure the position of a charged particle, or rather better, you want to measure some charge density operator in quantum field theory is mirrored over a small volume with a test function. This small volume is the volume occupied by a molecule in the liquid of a bubble chamber. You think of a single molecule. Now, this molecule can be in two states, non-ionized or ionized. You forget the rest. This is an oversimplification. If the molecule is not ionized, your system read nothing. The particle is not here. The charge is zero, whatever. If the molecule gets ionized, then your cosmic ray passes away very quickly, But after it passes, this ionized molecule gives rise to the formation of a bubble, because it's a perturbation in your metastable liquid, which was a liquid artificial but wanted to be a gas. And then it seizes this occasion to become a gas, and the bubble is formed. This is an irreversible process, yeah, which takes place in a little bubble, but it's a genuinely irreversible process, which has nothing to do any longer with your observed particle, which has passed away. So this is just an interaction between the microscopic part, the molecule, and the macroscopic part, which is the surrounding liquid. Okay, now note also an important point, that we don't have to make any transition from classical to quantum. You treat this macroscopic part also quantum mechanically, but the point is that you will have a dependence upon the number of particles. Yeah? You have that after the measurement, your state, if the system was already in an eigenstate of Ej, your state will be a tensor product of Ej psi with psi j, the microscopic part, red, the value j, tensor with psi j prime of n, which is the state of macroscopic part of the apparatus, amplification of the fact that the microscopic states are in the state psi j. Yeah? And as n, this is the center point of Daneri-Lorenz-Prosperi, as n tends to infinity, the state induced by this vector psi prime j on whatever algebra you had, yeah, will tend to states of different phases, yeah, which are disjoint representations. Yeah? So the phases will be completely lost. It will be, the result will be a mixture, because these states, the limiting states, are one liquid and the other gas, yeah, of an infinite system, because you approximated the number of components by infinity. Yeah? You took the thermodynamical limit. If you did not take the limit, there will be certainly, how do you say, interference terms, but it will be so small that it will be absolutely impossible to measure them, so no information of the phases can be retrieved. Yeah? I mean, to retrieve that information would be the same as asking yourself, how long do I have to sit in this room in order that all the molecules of this gas, pack them together in a corner and we just suffocate because there is no air. It may happen, yeah? But don't be afraid. You can, if you want to wait for that event, you have to wait several times the age of the universe. Yeah? So we are pretty safe. But the same thing would happen for the measurement. Yeah? So this is, to me, a very convincing explanation of the decoherence. Now I want to come to the main point, yeah, of this talk. This is always a main decoherence. By the way, we made already this approximation that T is much smaller than 1, yeah? And then we made also this approximation, n goes to infinity to get the transition from pure to mixed, yeah? In practice, of course, T will not be much smaller than 1, but will be infinite. I think we discussed that with Rudolf very long ago in Rome, yeah? And we decided that measurement process was something impossible to treat exactly, because it's always based on a scattering process. The infinitesimal process is really always a scattering process, and as such it would mathematically should require evolution from minus infinity to infinity, not to 0 to t. Yeah? So this is a very hard, very sharp approximation. Yeah? But the main point is another. Yeah? So, and before I mention that, I want to mention what I said about the bubble chamber can be repeated for scintillation counters, for the modern descendants of the Geiger counters, namely multi-wire drift chamber counters, all that. They all work in the same way. You have an irreversible process, which is launched by some microscopic effect, which is the detection of the particle or whatever. Yeah? Anyway, the main point is the following. I said that you have these 3 Hilbert spaces, but this is all right in quantum mechanics of finitely many particles. Now, if you are in quantum field theory, you don't have 3, you have 1. You have 1 Hilbert space which describes all possible situations. Describes your system, which is some specific quantum state of the fields, or you have to add with some creation operator, the microscopic part of your apparatus, or with a huge creation operator, a product of 10 to the 23 field creators, whatever, you have to add to that in the same Hilbert space also the amplifying part. Everything lives in the same Hilbert space. As a consequence, the time evolution is not something you can invent as in the model von Neumann, but is given once for all. Yeah? But even more important than that, your microscopic part of the measuring operators and also your macroscopic part have to be somewhere. They cannot be some global thing floating in the air. Think for a moment of the von Neumann picture. You can describe the addition to A of the microscopic part as an isometry, which sends psi to psi tensor of psi r. And of course, if you add also the macroscopic part, you have a similar isometry to add more. The time evolution in the approximate sense I discussed before is described by sending this isometry in the Heisenberg picture when you compose it with Ej, which we ought to commute with it, of course, in the previous picture, to Wj Ej, where Wj is another isometry, again commuting with Ej, actually all observables, which sends psi to psi tensor of psi j. Yeah? Now, in quantum field theory, these isometries should be elements of the quasi-local algebra. And as such, they cannot commute with all observables. Actually, I said commute, I should have said intertwined it. They intertwined observables into different implementations. If they were intertwined as for the observables, for all observables, it would be just a multiple of the identity. Yeah? And the vacuum would be not changed, which is not possible. So, in brief, this W and Wj have to be somewhere. And now we come close to a point that we always kept closed in a shelf and never discussed that in quantum field theory. I would like to say that, quoting this, that eingespenst geht in der Welt der lokale Quantenfeldtheorie. With people who are not too young will know this quotation. Certainly you know it if you are 150 years old, yeah? Because that's the beginning of the manifest of Marx and Engels. Yeah? Anyway, what is this, this ghost? This ghost is what is an operational definition of local observables. We never discussed that. What does it mean operationally to say that A is localized in O? Can you invent a process which measures something which is localized in very tiny region? The best I can think is of a region of order of few Compton wavelengths of a molecule, where I take the creation operator of a non-ionized molecule applied to the vacuum, and this is my system. If this creation operator is very well localized, this is the creation of the measuring operator for the position, in the sense I said. Yeah? This is the best I can think of. Anyway, this W and Wj have to be somewhere. And if you want that your observables who are localized in O, it's reasonable to ask if they are in the same region, at least the microscopic part. Of course, the macroscopic part can be localized somewhere else, but we also decided that the time needed for the evolution, which performs the measurement, is very small. So if you just change O by a slightly larger region, you can also say that also the time evolved, the alpha t of W is in the same algebra. Yeah? Now, the effect of this statement is rather dramatic. Yeah? W is this isometry which creates, acting on the state vector psi, state of the system in psi plus the microscopic part of the measuring apparatus. So it will be in practice, for instance, if your molecule was just one, well, it will not be hydrogen, it will be some more complicated gas. Well, it will be just the creation operator of the appropriate baryon number and zero charge of the molecule strictly localized in a small region. Of course, if the molecule is ionized, it will be no longer strictly localized because the well-known problem of localization of charges in quantum field theory. But it will be approximately localized up to epsilons. If you use the cluster property, what I'm going to say will still remain unchanged. Yeah? Anyway, so you have this picture, yeah, that And this is what I just said in words. Yeah? This is exactly the situation. And I also warn here with this curly sign of dangerous turn that it is not strictly localized when it is charged. But anyway. Okay, so let me jump what is not essential. The main conclusion is that W is in O, and also alpha T of W is in O, which means that if you take now your state omega, whatever it was, and you measure A, this observable localized in O with finite spectrum whose spectral projection were EJ, etc., yeah? Then the state with the microscopic part of the apparatus added before or after the measurement will all look, these three states will all look the same when restricted to observables which are spatially separated, because W will commute with any observable which is spatially separated, and then the effect will be nothing. Yeah? So the effect of the measurement will only propagate from the region O in the causal shadow of O. Yeah? And if you are out of that causal shadow, you will not know that the other projection has been measured, that this projection has been measured, you will see no effect. What does this mean? This means that, let me see, do I have to show this? Maybe not, because I have little time. Oh, and also I could add to this statement that the same will happen if you also add the macroscopic part, the amplification part, provided you go farther away, because the macroscopic part will occupy some finite volume. In practice, it will go from few microns to few centimeters. Yeah, but it could be also the size of the laboratory. But certainly, if you think of the EPR paradox, if you sit in Andromeda, all these regions, I mean, your instrument, your laboratory, the Earth will be a point, yeah? So it's the size that would not matter. And the same will happen if you take the composition of these two isometries, creation of the microscopic part, plus the creation of the macroscopic part. Yeah? And then the state, the resulting state, if you go really very far in space-like direction, will always look the same. What does this mean? This means that if you have the classical EPR arrangement, yeah, you have your pairs of entangled photons being sent halfway between here and Andromeda 1 million and something years ago. Yeah? It arrives now, one arrives now here, Alice measures it, she finds some polarization left-handed or right-handed, yeah? And Bob is on the Andromeda, which does the same experiment, and Alice and Bob will find always a superposition independently whether the other one does or not the experiment, until one or two waits 2.5 million years until he enters or she enters the causal shadow of the other laboratory. In that case, he or she will see the correlations. So this is very heretic, yeah? But I must say two things. The first is that this is probably not new at all, because at least the conclusions were already proposed by Helwig and Krauss more than 30 years ago, the beginning of the 70s. And I'm told that Rudolf has important comments in the second edition of his book that he do not possess, yeah, on the measurement process, which might even contain the same point. So it was very risky to expose this without having gone and seen first the second edition of your book. Yeah? On the other side, one must compare with experiments, because there is marvelous experiments of Aspect where he's able in his laboratory to deal with space-like separated events, but this very smart technique of using polarizers which change so fast in time that they change faster than the time one photon employs to reach one side, from one side to the other of the instrument. Yeah? But his photons travel in waveguides. These waveguides define a Lorentz system which is there. I mean, to believe in that result, I will wait until Aspect does the same experiment to satellites and the photons travel in the vacuum. They are really disjoint measurements. But I must say that as all hereticians, yeah, once I reached this conclusion, I found for the first time in peace with myself. I thought that this corner of quantum mechanics was something which always disturbed me deeply. I could not believe in the EPR setting, but they could not understand what was the wrong point. To me, this is a reasonable picture. I'm quite satisfied with it. Probably I'm not new, as most hereticians. They don't say new things. But all hereticians have a common feature. Once they reach the believed, they keep it firmly. You know, the last words that Giordano Bruno was allowed to say was muoio martire e volentieri, certo di non aver nulla dei miei pensieri di cui pentirmi. I'll die as a martyr and willingly, and I'm sure that there is nothing in my thoughts I should regret about. And this is the reason why he was sent to fire with the iron mask in such a way he would not speak to the people, because they did not want him to repeat these things. Anyway, in the same way, now I'm in peace with my consciousness until the aspect experiment. I understand it well, say, because it might well be that if I study it more carefully or somebody explains to me, I will have to take it back, but or new experiments are done. But I would like to stress in conclusion these points. The usual picture is the resulting of these three limits. You have to take the volume occupied by your instrument going to the whole space-time, the time of the interaction going to zero, and the number of particles according to Daneri, Prosperi, and Loinger go to infinity. And it's even doubtful that you can take these three limits together, because they're somehow in conflict, but I will not enter in this detail. My point is that these three limits are a reasonable picture if you deal with non-relativistic quantum mechanics with the final number of particles. Then it's quite good. So I'm not questioning at all quantum mechanics. So quantum mechanics is, to me, the most sacred realm of our knowledge so far. I'm just questioning the interpretation of the measuring process, which, in my view, is pushed too far beyond those limits. If you forget about these limits, you meet the paradoxes. Actually, the fact that this limit is needed already appeared long ago in the work of Araki and Yanase, where they pointed out that additivity or angular momentum is in contradiction with the possibility of measuring the classical sense. Okay, I should end just adding some references to what I said. I think the first important reference is Daneri, Prosperi, and Loinger. Then there's this paper of Helbig and Krauss, which does not seem to use my picture. It's not identical, but they proposed the conclusions. They proposed the same conclusions. Then there's some paper by Aronov and other people. Then there's the paper of Sewell, which takes up the point of Daneri, Prosperi, Loinger, and makes some computation about the exact decoherence only in the limit n goes to infinity. And the paper I wrote here for curiosity, the free will theorem of Conway. There's some paper on stochastic quantum mechanics and measurement process. But also I should mention about the existence of, I mentioned this point earlier on, that the existence of entangled state is not at all in contradiction with locality, because in quantum field theory you can construct very easily entangled state, and this can be found in much more detail in the papers of Summers and Werner and Werner and Wolf, which I quoted here. And so I think I passed largely my time, I don't know, but let me just end showing you a picture of our father.
Well, thank you for this beautiful expose. You did go over time a little, so let's have very few and very quick questions only. Yes?
Yeah, I had just a short comment on Sergio's beautiful slide about light. In our book, Mathematical Foundations of Gauge Theories, written with Professor Giovanni Martucci of Firenze, we begin with a poem with title In the Beginning. The first stanza is, then God said, let there be gauge theories. And there was light, clear and bright, followed by particles, fundamental or otherwise.
Very nice.
All right.
I would like to comment on those convenient variables. So usually those arguments implicitly assume existence of quantum gravity and interaction of gravitational fields. So instead we can just have on the market some models of quantum gravity. Some of them are simplified, some of them take into account all the degrees of freedom, although they may be not physical because they assume existence of some matter fields like gravity. Kuhar matter, which may be non-physical. Nonetheless, from the mathematical point of view, there are models of quantum gravity, and we can just check if the quantum structure defined by the operator of gravitational field in those models agrees with our heuristic expectations or not, and what it is.
And did you do that? What's the result?
No, because I'm not working on
So please. Okay, if you want to do that, I'm interested in the result, but I would tell you that if you don't find this, I would say that your model is wrong.
Let's leave it on that note. According to Henning, we will resume 20 to 4, so 10 minutes past the schedule. But let's thank Sergio.
Thank you. Thank you. Thank you for not having interrupted. I did not realize. I did not realize I was so late.
So much to say.
But you know,
Yes.